So welcome everyone. I hope you can all hear me. Welcome to our today's discussion titled Gas Lift Theory and Practice. Let's give it a few minutes as I can see more people are joining us. We have 95 people now. And in the meantime, I would like to ask the Greek people that have joined to please edit your name in the English way so you can receive the certificate of attendance. It will be easier for us to send to you. My name is Marios Ekretidis, and I will be the moderator of today's discussion. I'm a master's student in petroleum engineering at Technical University of Crete, as well as the president of our SP student chapter. And I would like to thank Online Petroleum Academy and engineer Ahmed for offering this webinar for us in order to transfer knowledge from the industry to all of you who attend. OPA, for all of you who haven't heard of us, OPA is an organization offering training courses and webinars for petroleum engineers and geoscientists in different aspects of the oil and gas industry. And Technical University of Crete SP student chapter has been established in 2018 in Crete Island here in Greece. So before we start, I have to mention that this meeting is recorded and will later be uploaded to both of our YouTube channels, so you can watch it at your own pace and get the maximum benefit out of this. We kindly ask you to keep the microphones and cameras switched off during this meeting. Of course, you can all ask. Actually, we invite you all to ask. All your questions should be addressed at the chat box and will be answered at the end of the presentation. Today's session will last approximately 1 hour to 1 hour and 15 minutes. And please keep the chat professional at all times. So at this point, it's after 7. I believe we have enough attendees to proceed. So I would like to say a few words about our speaker. Our speaker for today is engineer Ahmed Gaber. He's a senior petroleum engineer at GAPCO. GAPCO is a petroleum company and Gulf of Suez petroleum company. He got his bachelor degree in petroleum engineering from Suez Canal University in Egypt in 2011. Engineer Ahmed has presented a couple of technical papers in Egypt Petroleum Show in 2019 and 2017. He has also volunteered as an instructor for gas lift and well modeling using Prosper for both SP Egypt and PDP Egypt. He was the technical manager for SP Egypt Young Professionals in the season 2017 and 2018. So I hope you can all listen. You can, about the chat, I see what you're writing. You can just edit your name. You find yourself, and from the 3 dots, which is more, you can choose rename, and you can name yourself in an English way with Latin characters. It's pretty easy. So without further ado, Engineer Ahmed, I believe we are ready to start. And if you are ready, the mic is all yours.
Hello, Marios. Hello, everyone. Thanks for this nice introduction. And thank you all for attending today's webinar. Actually, I encourage and I like that from time to time, people always try to improve themselves. And actually, this is a good way always to spread the knowledge and know about other culture and other studies. So today, our topic is about gas lift theory and practice. So what's our content today? We will speak about nodal analysis in brief. Then we will speak about artificial lift methods. Then we will speak about the gas lift concept. And then we will go to speak about what are the types of gas lift. Then for sure, we will go about the equipment. And I'm pretty sure that a lot of you have heard about the unloading, so we will discuss what will be the unloading procedures, the gas lift design, evaluation, and we will end with a case study. So I hope that this webinar will be beneficial for you all, and hope at the end we will have a lot of discussions and questions. So this schematic is like an introduction showing our system. So we are all petroleum engineers, and we understand that we have our reservoir here. Fluids are moving through the reservoir from the high reservoir pressure into the well bore. Then it moves along our completion, going up along this completion till we reach the wellhead. Then it moves through the flow lines until we reach our separator. Usually the where we have pressure. Normally it's like 70 psi, 100 psi, and we have then the fluid moving through this flow line, which define our wellhead pressure in order for the fluid to move into this direction. And then if we have a fluid that's moving, if we have a fluid that's moving through the tubing, it have a certain pressure losses, which give us a certain BWF here and a certain reservoir pressure here. So we will see in details what about the nodal analysis. So in order for the fluid to move in the reservoir, there must be a drawdown. It means here, the pressure here must be less than the reservoir pressure here in order for the fluid to move into this direction. So depending on the productivity of the reservoir, we will have a certain rate. So if we look at this curve, this is the curve, the inflow performance relationship, which is the relation between the pressure at the bottom hole and the flow rate. So when we start at the reservoir pressure, it means that the BWF, when it's equal to the reservoir pressure, it means there is no drawdown. It means that there is no rate. As you increase the drawdown more, it means that you will have a higher flow rate until we reach here something we call the absolute open flow, which is the maximum flow rate. It means like we have a BWF equals 0. It is theoretical, which means we have the maximum drawdown. So this curve is the IPR curve is describe the productivity of the reservoir. How, for example, if I have a reservoir with high productivity, I need only low or less drawdown in order to produce high rate. As example, I have a reservoir with a productivity index of 1. It means in order to produce 1,000 barrel of oil or 1,000 barrel of fluid, I need a drawdown of 1,000. But what if I have a reservoir, its productivity index is 10? It means in order to produce 1,000 barrel, I need only like 100 psi as a drawdown. So for me, the most important is to understand this curve, and there are many factors affecting this productivity, which is the permeability of the reservoir, the height, the skin, also the viscosity and the oil volume factor, which describe the reservoir characteristics. The other relationship, which is important for us to understand what's going next, is the outflow performance relationship. So for, let's go backward to this slide. In order for the fluid to move from this up till the top, it means it will encounter some pressure losses. First, the pressure here must be higher than the wellhead pressure. So first, you encounter or having to face the wellhead pressure loss. Also, as you are moving, there are some friction. This friction is a factor of the fluid rate. Also, as you go up here, you are moving against the gravity. So you have your potential energy. And there is another item which is like acceleration losses, but this item is always minor. So as we see here, it's like I have two main parameters. I have the, one second, I'd like to remove this a little. I have the hydrostatic or pressure losses due to hydrostatic and the friction, and I have this curve. Like as I increase the flow rate, I have to increase the BWF. So this is the outflow. This outflow is also having some factors. Without reading here, we can imagine it always depends on the profile in which the fluid will move. Wellhead pressure, the fluid characteristics itself. If a high viscous fluid is moving, it means that the pressure losses will be higher than if it's, for example, a light fluid. And this comes to this slide, which is the production. When production happens? Production happens when I have my inflow is intersecting my outflow. Means I have a certain drawdown at the sand face. So the reservoir is giving me fluid with a certain rate. And in the same time, this fluid is going through the wellbore up to the surface with certain pressure losses. So at this point, I have my equilibrium. I have a certain fluid rate, and this fluid rate is combined with a certain BWF. So if I look at this curve here, I understand that my BWF is here and I have this drawdown. In the same time, I understand that my losses inside the tubing will be plus the tubing head will give me this BWF. So this is my IPR curve, and this is my outflow performance curve, and this is intersection. So normally, if I have a well and it's produced naturally, I have this intersection. This intersection will tell me at which rate I produce and what is my BWF. So when curve changes and when this curve change. For example, if I have a different reservoir pressure, I will find that this curve will change either up or down. Also, if I have different tubing head pressure or different water cut or whatever, this curve will change up or down. So the next slide will make it clear. In certain cases, let's imagine I started with this situation. I have my reservoir pressure, and this is my productivity index, and I have this outflow performance relationship for certain water cut, gas oil ratio, and tubing head pressure. Then by time my reservoir pressure decreased. It means this curve, it was here before, but now it's here, it's down. So I understand here the two curves are no longer intersect. What does this mean? It means that my well will not be able to produce. So what can I do? What can I do to make this well produce? I have to do one of two things. Either I can change this curve, the IPR, to bring it up again, or for example, change the productivity index itself, like rather than the curve is moving into like this, it can move into another direction. Like I made stimulation for the well, or I can change the position of this outflow performance. So this is what artificial lift is doing. Artificial lift methods are changing this curve, the outflow, in order to make the intersection. Like this. For example, I have my outflow like this by introducing artificial lift. My outflow can be this or this, depending on my design and depending on the type of the artificial lift I used. So from this curve or from this charts also, we understand is not only about making a well that's not capable to produce. It's also to increase the rate of the well. For example, imagine this well, the white, this IPR and this VLB, okay, the outflow performance relationship, VLB. Imagine this well is producing with only like 200 and it's not economical for me. I want this well to have more rate. So I can introduce a certain artificial lift method in order to change it from this to be like this. Here it will be like produce 1,000 barrel or like produce 2,000 barrel. So with artificial lift, I can do one of two things. Either a well that's dry, that can produce naturally, I can make it producing, or I can increase the rate of the well itself to be more economical. So this is the concept of artificial lift. So what are the types of artificial lifts and which type it's better to choose? So this is a screen showing different types of artificial lift. We will go quickly through them because we have a lot of things to say about gas lift, our main concern today. Maybe later or next time we specify another artificial lift method to talk about. So this is the sucker rod pump. The concept is we have here a chamber and we have a rod here. This rod moving up and down, so it forces the reservoir fluid to enter this chamber here. Then it forces it to go through some valves here up. It changes it give it, it's pumping it, it's giving its energy to go up. Another method here is hydraulic pump. In this, we have a high pressure fluid. It goes down, it make a pump moving. Then this pump is introducing energy to the reservoir fluid to make it goes up. We have the ESP, the electrical submersible pump. So the ESP is using a motor. We have a motor down here. This motor having power through electricity. This motor is moving and it makes a pump here moving. When the reservoir fluid enters this pump, the centrifugal energy is given to this fluid and the energy changes from potential to the kinetic to potential and the fluid is going up. Another type which we will talk in in details about it is the gas lift, and let's speak about it in the next slides. And the other one is the PCB, which is the progressive cavity pump. It's here we have a rod, we have a stator. The rod is moving and it delivers energy to the fluid. So here I'm not going into detail. I'm just trying to speak generally about methods that for me, the most important to know that we have many artificial lift methods. The most famous, you will find that it is the ESP, the sucker rod, and the gas lift. The PCB is used mostly when we have a high viscous fluid or when we have sand production and when the depths are not very high. So which artificial lift method do I have to use? It's better to use this method or whatever method. So there is a lot of things that make you goes into a certain method rather than another method. So if we look again into this curve, you will find that the sucker rod having here a high or a big surface load print. It need like high or big space. So I will speak about my company, Gapco. Gapco is one of the biggest offshore companies in Egypt. So most of our production is coming from offshore wells. It means we have a platform in the sea. There is not in platform. There aren't a lot of space. So for us, in order to introduce something like this is not possible. So for me, the artificial lift method, the sucker rod pump as artificial lift method is not there. ESP, for example, is needing electricity. You need a source of electricity. So in some remote platforms, we cannot have a source of electricity. So I cannot have this. Gas lift, as we will see in other slides, it's required to have high, like initially high capital cost. So, but running cost is very cheap. So, and at the same time, it doesn't require a lot of equipment. So as I will showing in the next slides, we use gas lift for certain reason. So for me, I want to deliver the message that we have many things that make me going into this or this or this. For for an example, the second road, the capital cost is low to moderate, but it need a space. In the same time, it can produce very wells with very low rate. On the other side, the ESP can produce wells with high rates, but the problem, the lifetime of the ESP is not very high. At the same time, it's very sensitive to gas and sand. The gas lift, as we will see, it's very tolerant. It can accumulate sand production. It can accumulate gas. But the problem, it requires high capital cost. So now let's speak about the gas lift concept and understand when do I use gas lift and what is the benefit of it. First, gas lift, this is the schematic of the gas lift. This is a normal well, like if I'm producing from a normal well, normally we have our production tubing, we have like a bucker here, and we have the Christmas tree, and production goes along the Christmas tree into the flow lines. If I have a gas lift, I introduce here a new line, the gas injection line, okay, where the injection gas, this gas is high pressurized gas. It goes through the annulus here into the valve here, and it mixes with the production fluid that going up, and both are going up and into the manifold and into our separator. So the benefits of the gas lift is low cost. I don't need the equipment here. You see, the only change I made to the tubing that I have something like called mandrel, like I have more or big size at this certain places, and I introduce a valve. This valve is normally cheap, and we will talk in details about this valve. And if I want to change this valve, go up, go down, I can go with some slick line, very cheap, change this valve with another valve. I can control at the surface the rate at which I inject my gas, and I can also control my production rate. If I have sand production, it's not a big deal. Also, it's very tolerant to deviation. It's okay. In GAPCO, we have wells with 90-degree deviation, no problem. The operating costs are very low, are relatively low. So what is the disadvantage or the main disadvantage is this. In order to have gas lift, we need to have high capital cost at the beginning. We have to have our system, the surface gas lift system. So this is the main concern, or this is the main constraint. In GAPCO, because we have, as I mentioned, we have a lot of wells. All our wells are like offshore. So previously or before, we have built this surface facilities, which enables us to do gas lift and make us very tolerant. And the gas lift operating costs, as I mentioned, are not very are cheap relative to other artificial lift methods. So what is the surface facilities? How does it happen? We have the well here. The well is producing well fluids. It goes into a production facility, production manifold. We have many wells, this well, this well, this well. All production is going to production manifold. Then it goes to the separators. In the gas and oil separators, the produced gas is goes this direction, while we take away the produced water and the produced oil. Please bear in your mind that normally the wellhead pressure is not high. Normally the wellhead pressure is like 100, 150 to 100 psi. And normally the separator pressure is like 170 psi, 60, something like this. Please bear this in mind. So the gas is produced normally with low pressure. Then this gas going here into a certain station where they removed the hydrate from this gas, and then have that this gas is compressed. We want to increase the pressure of the gas to be higher than this, because normally the gas injected gas, as we will see later, it's injected with high pressure. So I will give you an example. For example, here in Gapco, we normally have the wellhead pressure about 100, 150, and we have the injected gas about 1100, about 1100 psi. And in certain platform, we have a different injection pressure. The injection gas pressure is like 1500. So the gas is compressed here. It's unfiltered from hydrates and from any particles, and then it goes to the injection gas manifold, and it goes into the annulus, and it's injected here. So now we understand why we are using gas lift, its benefits, and at the same time, what the constraint is the system itself. So what are the types of gas lift? Normally we have two types. We have the continuous gas lift and we have the intermittent gas lift. So normally what happens, we inject gas from the annulus here, and we have many valves, and I will describe later why we are having many valves. And then we inject gas continuously through this valve. This is our operating valve, and gas is mixed at this with the fluid until it moves up and produced. So this is in a continuous basis. So all the time, gas is injected from here, and oil is producing, and the oil is producing, and they are all mixed together and going up. This is done continuously. Another type is intermittent gas lift. So from its name, intermittent means it's like doses, like slugs, like I'm not injecting all the time. Sometime some fluid like this is built up, some pressure inside the tubing, and at certain pressure, gas is injected from here to make a certain slug of gas, and then until the pressure here reached a certain value, then this injection gas stop. This slug goes up, giving time to another slug here to be happened, and then the injected gas is opened and it happened again. In a simple way, the gas here, the injection gas is not continuous. Why is not continuous? Because some wells are very weak, like the productivity index of this well is very low, so they cannot produce continuously. It's like they take some times to make some slug, then you inject some gas, mix it with this slug, it helps it to goes up, and then you close the gas until some time another slug is built up and something like this. So normally most of the gas lift is the continuous. In also on very low certain cases it's something like this. So our concern now through the rest of the presentation or the webinar will be about this continuous gas lift. So what gas lift is doing? As I mentioned, we injecting gas here, high pressure gas, it goes down, it mixes with the fluid coming here from the formation and then go up to the fluid. So how about the pressure? What happens? Normally we know that we have the pressure traverse curve or the pressure gradient. As I move up, I must having a fluid gradient. Like I have a pressure losses through the well pool, okay? And this gradient is depending. If I have like oil, it's be like 0.3, zero point 0.2. If it's gas, 0.07, whatever the gradient. So this gradient is depending on the gas oil ratio and depending on the water cut and depending a lot about the rate and many things. So this is the gradient of the fluid of the formation fluid. It is a gradient from the formation fluid going up. Like it is the pressure losses as we go up. until the point of injection. At this point, I'm introducing gas into the system. Like at this point, the GOR here is bigger than the GOR there. Again, I'm producing a well. I will answer all the questions inshallah later when I finish. We have good time for questions. So again, as I mentioned, fluid is moving up here with a certain gradient because I have, one second please. No, not now. So again, I have my reservoir fluid is coming up with this gradient with certain GOR, then gas begin to be injected here. The effect of gas, it decrease the losses or the pressure losses as I go up. So it changes the curve rather than going into this direction to go like this. Normally you'll find that we have here like 0.2 or 0.3 psi per foot. When the gas lift is introduced, we have less gradient like 0.1 or 0.15. Video is coming and showing it better. So this is my well, and this is the gas lift mandrel. As we see, we have a normal tubing, but this tubing has certain places where the size of the tubing is bigger. So here, normal tubing, but here we have certain places with bigger size, and we put in this gas lift. Here, the gas is going through this port, and it's introduced down and going into, again, this is annulus. You see, this is our reservoir fluid, and at the point or the operating, it's mixed with our injection gas. So the injection gas is lightening or reducing the pressure losses. The next slides will make it more clear. I will be back again to this slide, but the next slide. So if I have fluid inside the well bore, and this is fluid is not moving, I will have certain gradient, static gradient here, and the pressure is equal to the reservoir pressure. So here is two scenarios. If, for example, I have this well is producing with a certain gas liquid ratio, I will find this is the curve. This is the pressure traverse curve, the losses, the gradient due to this movement of the fluid into the well bore. So what actually gas lift is doing? Gas lift is like I'm moving with this gradient till the injection point. But then after the injection point, now I have a new gas liquid ratio. So my pressure losses starting from this point is less than the actual pressure losses. Again, if I'm producing, for example, with 500 or 300 gas liquid ratio, standard cubic feet per barrel gas liquid ratio, I will have my pressure losses something like this. So I must have this BWF. I only have this drawdown in between in the reservoir. But when I introduce gas lift, what I do, I decrease the gas liquid ratio starting from the point of injection. The effect of decreasing the gas liquid, increasing the gas liquid ratio is that it decreases the pressure loss, which means it makes me produce with less BWF. So it gives me the opportunity to have higher drawdown. It gives me the opportunity to have more production rate. So the gas lift, again, the concept of the gas lift is that I inject gas at a certain point. Starting from this point, I have a gas liquid ratio more than the gas liquid ratio of the well. So I have less pressure losses starting from this point, which means I can have less PWF here. It means I can have high drawdown. It means I can have high production rate. Or in another case, if the well is dry and I cannot produce it, I can produce it. So this is again what's actually happened. I have the well producing with this rate till this injection point, and then it has another flow gradient till the tubing head. And this is my casing pressure. It is the pressure of the gas inside the casing here. The gas here is injected with high pressure here, and it increases with a certain gradient. This gradient is very low. It's 0.03 psi per foot. It is the gradient of the gas itself until I reach the injection point here. And I have, as we will see later, a pressure drop, like for the gas to enter the tubing, it must have a pressure higher than the pressure inside the tubing. Here, in order for this gas to enter here, a pressure here must be higher than the pressure here. It's like 100 or 150 or 200 psi difference, and it depends on the size of the valve and the injection gas and many parameters. For me, the most important to understand the concept. So again, what actually did I do? I had a well like this. I changed the VLP of this well by introducing gas lift because I made the gas liquid ratio higher. So if I increase the gas liquid ratio or injected more gas, I will have more rate. But is it till the end, like I can increase the gas rate and all the time I will have higher gas liquid ratio and all the time I will have VLB going into this direction, so I will have a high rate? No. I have a Q maximum, or we can say it like the maximum or the optimum, the maximum injection gas rate, like more than this injection gas. On contrary, I will not increase my rate, but I will lose rate because the more gas I increase, I will have more friction losses, and it will end that my VLB will be on the other direction. On another way, we can show it like this. My liquid rate is increasing as I'm increasing my injection gas. Injection gas is increasing, my rate increasing until I reach a certain point with the maximum liquid rate. After this point, when I increase my injection gas, then the liquid rate will start to drop. So normally, which injection gas I choose? Normally, I choose something like this, the economical or economic optimum gas injection rate. It means like I try to optimize. I try to use an injection gas that give me the highest or nearest to the highest rate, because sometimes, for example, here, for example, the injection gas is 2, and there the injection gas is 4 or 5. But in the same time, the increase in fluid rate here is not that much. So, like for example, if I, for example, let's say number, here I produce with 2,000 barrel. Here I produce with 2,100 barrel. So only like 100 barrel. And I increase it like 1 million injection gas from here to there. No, I can use this 1 million and open another well with higher rate. Anyway, for now, the most important to understand this concept that we have optimum or maximum injection gas and maximum liquid rate. So now we finished the concept of the gas lift and we understand it, okay? Then we will go quickly into the equipment. So we all saw in the video that we have this schematic, we have this tubing and we have this increase in the size of the tubing, which is called gas lift mandrel. And the purpose of this increase is to put certain valves here. Through these valves, gas is injected, as we saw in the video, the gas is injected here, and it goes down here, mixing with the fluid coming from this side. This is the valve. The valve having here a port and having backing here and there to put it here and prevent any movement of fluid into this direction or this direction. We want to force the gas move through this direction, and also it have a check valve here to prevent oil from going or fluid from going into this direction. And it has bellows, and we will speak now in details about what is the bellows or domes and what is the purpose of it. This we see valves in a different view. This is the port where the gas is injected from here. And we have a stem here. This stem is closing the port. This port is this, like gas is going from this port. So this is a stem, this is moving up, and here we have a dome or bellow. So we are charging this dome or bellow with a certain pressure. If only the pressure of dome is existed, you will find that this dome or this pressure is forcing this piston and this rod and stem to close this port. In order to open this port, you have to have force in the other direction. So what are the forces here? We have this dome. Here we have a pressure. This pressure is playing on this area, the area of the bellow. It forces this stem to be down. On the same side, we have other down in the well. We have other pressures. We have the casing pressure. Remember, everyone? Gas is injected here, the annulus here. So we have here the casing pressure. So we have the casing pressure working on this area, the area of the bellow minus the area of the stem or the port. And in the same time, we have a tubing pressure here is working or trying to open this. It's moving into this direction. It's working on this stem. So in order to open this valve, the force in this direction down, which is the force of the bellow, the force due to the pressure in the bellow, okay, must be equal to the forces due to the effect of the casing and the tubing. I will not go in these equations because I want to give you more information, but what I want you to understand is that we have this casing pressure is affecting this area. We have, when the valve is closed, we have the tubing pressure affecting this area and the casing affecting this area, and we charge the valves with a certain pressure, okay? And we will see later how we choose or calculate this pressure. So again, when the valve is closed, the dome is affecting in this direction, the casing is affecting up, and the tubing is affecting up. When the valve is open, we have the casing pressure is affecting on this, and gas is moving into this direction into the tubing. This, I will send you the slide to see this. This is we're speaking about the opening force and the closing force. I don't want to get in details to give you better information. But to understand, we only deal with the casing pressure. We deal with the pressure inside the dome or the bellow, and we deal with some parameters called A and B, and are the ratios of the area of the port. B is the area of the port to the area of the bellow, and A is 1 minus B. So it's only about the size of the port here and the size of the bellow and pressures there. Okay, so now we speak about the unloading sequence. First, why we are using many valves. Normally, as we saw in the video and as we saw in previous slides, normally we are injecting from one valve. Continuously, we are injecting from one valve. Let's imagine now this is the valve from which we are injecting. All the time, gas is injected here and goes into this valve and producing. So why we are having many valves? We are having many valves for two things. First, the first or the most important is unloading. Normally, you complete the well, you drill the well, and then you install your tubing and set the bucket and stuff like this. And the well is loaded with the completion fluid. You have to control your pressure. Then you want to produce the well. There is either one of two scenarios. Either I have only one valve here, but if I try to inject gas, it will not goes down because we need very high pressure to go down. And from the beginning, if you understand, we have a compressor system and we have only limited injection high pressure gas. Like for example, we have a high pressure gas of 1,500, 1,000 or whatever. So I cannot produce until I remove this fluid inside the well bore. So I can go there with coil tube and with nitrogen and I do unloading. I remove the fluid here until gas can enter here and produce, or I do something called unloading valves. I introduced many valves. The objective of these valves is to help step by step to unload or remove this fluid until my gas reach the point at which it will be injecting. I will show it here with this graph, and also I will show it here with a demo. So normally I have this fluid, the well is killed, so I have a tubing or the gradient of the completion fluid, and it lead me to the reservoir pressure. Then I started to open the injection gas. I started to inject gas with high pressure. So gas is moving into this direction. Normally, by the way, when the gas lift system or the tubing is there, all these valves are open. I inject gas here. This gas is moving this direction and push this fluid to moving into this direction and goes like this. Until this gas is reaching the valve number one. Then it's starting to mix with the completion fluid here in valve number one. And it began to decrease the pressure gradient here. As we will see here, first we have the reservoir pressure here, then here we started to have certain drawdown. And the fluid or the reservoir fluid starting to move and goes up. During this, my gas is here going gas into this valve, and at the same time, gas is pushing into this direction and push this fluid to go this until it reaches the second valve. Now gas is injected from this valve and this valve, these two valves, and helping to decrease the gradient here more until helping me to increase or doing more drawdown. Then I reached a certain value or certain limit where all my injection is going into this valve and this valve is closed. I reach this valve and all my injection gas is going to this valve and the upper valve is closed. And then I continue again. I'm pushing fluid into this valve, and at the same time, I'm reducing the fluid gradient here until I reach this third valve. So now I have two valves open, the second valve and the third valve, and this valve is closed. Gas is going from here and from here, and by time all gas is going from here, and this valve is closed. So if we again trying to conclude this, from each time I'm injecting through a certain valve, then decreasing the gradient here, then I go to the lower valve until I reach a certain pressure limits. When this valve is closed and I inject only from this valve, then I go down from to this valve and this valve. I have two valves open. Then a certain limit come when I inject only from this valve and this valve is closed until I reach my operating valve. In this case, I have only this valve is my operating valve, so it's okay. So this is the case. All the time, I'm injecting gas here with this pressure until gas is reach the depth of the third valve. It goes into this valve up, mixing with the formation fluid coming inside the tubing. We have this pressure losses, this blue one. As we mentioned before, the gradient here is the gradient of the fluid until I reach the point of injection. Then I have another gradient because starting from this point, I have a different gas liquid ratio. And all the time I having this, I'm producing this continuous way. I can show you quickly a demo that showing again what's actually happening. So normally I have this curve, this chart, these lines. The well is closed. I have completion fluid in the well until the reservoir pressure. The injection gas is the red line. The blue line is the pressure inside the well pool. Bear in your mind, I want to reach this curve. I want to produce my fluid like this, and then this, I want this to be my point of injection. So we will understand now what's going on. I begin the unloading. Gas is starting to moving through this direction. It pushing the fluid. You see, as I'm pushing the fluid, my pressure is increasing. Like here, if I have a gauge here, I will find that my pressure is increasing until it reach my maximum pressure. I made the design that my maximum pressure will allow me to go to the valve number one. So here, gas is going into this direction, mixing with fluid, reducing the tubing pressure and making drawdown here until I reach the valve number two. Now I'm injecting. When I reach this valve, I'm injecting from two valves, from this first valve and from this second valve, until I reach a certain value where this valve is closed. I'm only injecting from this valve. And this will happen again. By the way, this blue one is the tubing pressure that is changing as I injecting. Take our bear in your mind that, 1 second, I want to show you this. If we all, 1 second, if we all take care, we will see that we started injecting high pressure gas here, and now we are injecting with this high pressure gas here. As we see, it's continuous until, and also I'm producing from this valve, I'm injecting from this valve, only injecting now from this valve, and I go down, injecting from these two valves. Sorry, I cannot answer all the questions, but after the webinar, we can get into the questions. until I reach here. You see, I having both. I'm injecting from both wells and from both valves until I reach the point at which I am injecting. And this will be my operating point. All the time, I will have something like this. This is my operating point. I'm injecting gas here with this pressure. Like if I go and put a gauge here, I will find the pressure at the casing is this value. And if I go here with some gauges, I will find that this is the pressure traverse inside the tubing here, and this is my drawdown. So take into consideration, I started with injection gas pressure here, and then is decreased. Why? I made this calculation in order to prevent many valves opening in the same time. On another way, first I was injecting from here, I was injecting into this valve. Then I was injecting from two valves, this valve and this valve. I was injected with this pressure, sorry, until my casing pressure decreased, and now I'm injecting with this pressure. When I inject with this pressure, the first valve will be closed because it's designed to be open with this pressure. I will show it this now when we go to the gas lift design. I tried to make it clear from here, but no problem. The most important for me that we understand now why I am using unloading valves, what is the objective of them, and what's actually happening. So what is the meaning of gas lift design? What is the objective of doing gas lift design? The objective of doing gas lift design is two things. First, I have to set or to put the places of the valves. Where, first, how many valves I need. Second, where to put these valves. Also, these valves, what will be the below charge of these valves. But before I start with this, I want you to understand that we have many different types of valves. First, normally, I want to reach this curve. This curve is the curve that I am producing a well with a certain flow rate. As we see here, it's like 570, with a certain gas liquid ratio, with a certain water cut and whatever. And I'm injecting gas. This will be my operating point here, okay? So at this point, or the valve at which I'm injecting, it can be either operating valve or orifice. Like it can be charged, it can be having this shape. 1 second. It can be something like this. I have the valve and it has a bellow, and this bellow is charged and this has a stem. Or I can remove this and it can be only orifice, like the gas injected from here and goes from here, because this is the point at which I want my gas to be injected. Or it can be operating valve like this. And there's something or another valves called whiskey valves or dummy valves. These whiskey valves or dummy valves is for the future. Remember this curve here. I have here 1, 2, 3, 4. Okay, so this is my operating valve. I'm injecting gas all the time from here and I'm producing here. Why I have another valve down here? We understand that we have 3 valves here because, or 2 valves upper, because these are the unloading valves. These valves are helping us to produce the fluid up to the surface. I have, and this is my operating valve, I have this valve which is dummy valve or whiskey valve for the future. In order, if, for example, my reservoir pressure decreased, so I can go down and begin or start injecting from this valve. So when I'm doing design, I bear this in mind. I try to have to choose where will be my operating valve, and if I have whiskey valve, I choose where will be my whiskey valves,
and I try to calculate how many unloading valves I need and what will be, how they will be charged. So actually it starts with something like this. This is the pressure traverse of fluid of a well with a certain fluid rate. Again, what this means, I want to produce a well with 2,000 barrels, for example. This well having the formation gas oil ratio is like 500, and starting from the point of injection, which will be here, I will inject gas with to make the gas oil ratio 1,000 or 1,050. So I have this curve. I wanted to reach this curve. And I have a certain tubing pressure. Again, I having a well. I want this well to produce with a certain fluid rate. So I have my fluid rate, I have my well, I have my required tubing head pressure and the injection gas required. And I draw this curve, which can be from correlations or whatever. This is the curve I want to reach. This is pressure here, and here is the depth. And I have another curve. This curve is started with, this is the kickoff pressure or the pressure of the gas inside the casing. It is the maximum pressure that I can inject at the casing with this gas. So I mentioned before in the surface facilities that I take the gas with low pressure. I do compression for this gas to reach a certain high pressure. So I inject this gas here, and then inside the well, remember everyone, I have completion fluid. I have a fluid that's dead. This fluid, I put it to control the pressure, and we have this fluid with a certain gradient. Normally, it's like 0.45 psi before, something like this. So I have this fluid there, and I wanted to push this fluid to goes up and increase or inject gas. So the objective now from this, the first step is to uh, identify what will be the depth of the valve number one. So I inject gas from here. I have this tubing pressure. Normally, I take a safety factor, like 50 or 30 psi, and I go up, and this will be the depth again. I have this tubing curve, and I have this casing curve. I have the maximum casing pressure here, or sometimes I take like 100 or 50 psi as a safety factor from them. And this gradient is the gradient of the gas inside the annulus. It's normally 0.03 psi per foot. Then I draw this from the tubing head till the intersection here. This is the static gradient of the fluid in the tubing, the completion fluid. And I take a safety factor 30 to 50 psi, and then I put this will be my valve number one. So what will happen if I didn't do this? I took valve number one up here, or I took valve number one down here. If not, valve number one is down here, I will not be able to inject gas and produce, because this is my maximum gas and the gas that I can kick off the well with. So I cannot inject gas, the gas will not reach the valve, and the well will still dead. So if this valve is down, I will not produce, and I cannot be able to make this unloading process successfully. If the valve here is up, yes, I can do the unloading, but I will use more number of valves. The benefit or the idea of this design is to use the minimum unloading valves. I want to do this design. I want, for example, I will inject from a depth of 10,000. I want, before this injection depth or operating valve, I want the minimum number of valves. I don't want to introduce a lot of valves there. So this is the depth of valve number one. Same, we go here, we draw this valve, this gradient, sorry, the static gradient. We draw again another static gradient starting from this point, from valve number one till this point. To understand here what's happening, I have this gradient, I inject gas. By time this gas will decrease the gradient here until I reach a value. So from this point, I will have, from this point till the next valve, I will have only fluid inside the tubing. So I do the same. I want the casing or the injection gas to reach this or be able to go inside the valve and decrease the fluid column. So again, I do the same and take a safety factor and have valve number two also until I reach to valve number three. During this, I'm doing something called, I don't want to go in much detail because this requires a lot of time to understand. But the point is here, as we see, we have something called P casing 1, P casing 2, P casing 3. So I'm doing this and having different casing pressure in order to force that every time at the end of the unloading process, I have only one valve to injecting from. Remember, it's a demo. Certain time I'm producing from injecting from valve number one and valve number two until a certain value. Then the valve number one is closed. I'm injecting only from valve number two because at that time I'm reaching this BC2. Then I'm injecting from valve number two and valve number three until a certain value is reached, which is BC3. So I am injecting only from valve number three. So the concept of the gas lift is that at the end, I'm injecting only from one valve. So this is what I want to reach. This is my operating valve. I'm producing from this valve, okay? But I have before it three valves. These are used as unloading valves. First, I'm injecting gas through this valve until it's all there. Then I inject from this valve and this valve. Then after I reach a certain value, this valve is closed. I'm injecting from this valve until I reach my valve, operating valve. And at this valve, this is the only valve I'm injecting at all the time, and all above valves are closed. And sometimes I have something called whiskey or dummy valves. These valves used down here for future injection. And it comes with a table like this. In this table, I have the depth of each valve, what is the tubing pressure inside, what is the size of the valve, what is the charged bellow pressure, what the pressure that I charge the bellow or the dome with, and what is the temperature there, something like this. So I mentioned what is the unloading procedures, what is the gas lift design quickly, and now with something called gas lift system evaluation. Sorry if I'm speaking in hurry, but I try to give you a lot of information. So how to see? I said that the objective of the gas lift is that I'm injecting from only one valve. So sometimes we have certain problems. I'm not injecting from one valve, or I'm not injecting from valve number 4 here. I'm injecting from valve number 3 or 2, or I have multiple points of injection or whatever. So in order to evaluate our system, we are having something called gas lift survey. I'm going inside the well bore with pressure gauges, taking pressure at certain point and see how is my gradient inside the tubing. And at the same time, I have the gauge on the annulus and I can see my casing pressure, and I'm drawing this, and I have a gauge, a temperature gauge to see the temperature. As we see here, and as we can imagine, the effect of the gas is that it decreases the gradient of the fluid. So when I go here with the gas lift survey, I saw that I have a gradient here, and starting from this point, I have a different gradient. I have a 0.36 flow gradient, PSI per foot, and starting from this point, I'm having a different gradient. So I can conclude that this is my point of injection. In the same time here, I see that I have change in the temperature. So this is my point of injection. So through the gas lift system, gas lift survey, I can see what is my gas lift is doing well or not. I'm injecting from this point or not, or I have multiple points of injection. So what happened if I have multiple points of injection? This is a nice demo or a nice illustration. I will show you the demo. I have something called kick-over tool. The concept of this tool is to go down. It's open like this. It catches the valve and it goes up with the valve, changing it, and go down with another valve. And this is the benefit of the flavor of the gas lift. So here, so this is the kickover tool. I have a well. This well having a problem that I'm not injecting from valve number from the valve that I want to inject from. I'm injecting from a shallower valve. So what is the effect of injecting from a shallower valve? I'm not having the rate or the drawdown that I want. So I go down with this tool on slack line or wire line, and this tool, as we see, it goes down here until it passes this valve. I want to change this valve, okay? Then I go up. So the point here is to make this tool open and catch the valve. We will see here how this happens. This is a gas lift mandrel, as we said. In this gas lift mandrel, we have a certain groove. As we will see, it will allow, please, everyone, concentrate on this, what will happen. Here, as we will see, we have something like this. It forces, we have a pin here. It forces, when we go up, forces this arm to go into this direction again. As we see here, it orient like this until it go up, and this force this arm to go into this direction, and then I go down. Okay, I know from the tension that this arm is open. I go down, I do some jarring. Jarring is like, you know, with a hammer, something inside the tool's string. I do jarring, jarring, jarring until it latch with this valve, and then I pull it up. I do the valve retrieval. And as you see, I do jarring. Until it go up. So this is the kickover tool, and then I go with another valve on the kickover tool and set it here on that. So the last thing I wanted to share with you, it is something like a case study. Here I have this well post from a deep valve. We did this gas lift survey. This is the tubing, and this is the casing pressure here, and this on the right here, it's the temperature. So from this, I could see that the injection gas can reach valve number 6, but I'm injecting from here. As we see, the gradient here is the fluid gradient until I reach this value or this value. So I'm injecting from valve number 3. I want to inject from deeper valve. So I went down, we did gas lift valve change, and we reached it. As we see, the gradient, and I'm injecting all from down and be able to have the maximum drawdown. So this is the webinar for today. I hope that you all get the maximum benefit from it. And now I can go with questions. But if Marius or if Omar want to add or say anything, it's okay.
First, hi, and again, Engineer Ahmed. First of all, I would like to thank you. It was a very good presentation.
Thank you.
Indeed, a lot of information, but I think people have understood quite a lot. We have a lot of questions. But Omar, how we are with time, by the way?
I think we have 15 minutes, so you can go as much as you can in these 15 minutes.
Okay. So I would like to invite you, Omar, maybe to share in the chat box the links of OPA so people can attend in the future events, can find you, and I will share also our social media for future events. And you can also share the feedback, the survey. You can all fill the feedback. It's a small survey regarding today's event. It will be really helpful for us and OPA. About the questions, we have quite a lot. Engineer Ahmed,
Yes.
you're here? Okay.
Yes, I'm with you.
Okay, so I have a first question from Harilos Mariolakis here from our chapter. He says, what WPF number and above would be a good suggestion for intermittent gas lift?
Again, what's what?
WPF number.
BWF number يعني meaning what is the bottom hole flowing pressure to make
Yes,
intermittent valve?
PWF, like, yeah, bottom hole pressure.
Now, when do we use intermittent valve? We use intermittent valve when we have a well. We try to, for continuous gas lift valve, for example. Actually, we have this case, you know, we have a well. This well was a Karim formation, okay? Then we changed the formation and complete it into another formation. When we open the well as a continuous gas lift well, the well is producing for hours or 1 day, and then it dies. It don't produce, okay? So we suspect the reservoir pressure. So we go to this well and we measure the pressure, and we found that the pressure is not reducing. It's stable. So and then we made another survey, and we discovered that this well is very weak. The productivity index is very low. You know, like it needs sometimes to build up some pressure, and then you inject some gas, and then it produces. So normally this happens when you have a well, it producing very low rate, and it's producing with very low BWF. Then, and you cannot, and you already try to install or try to make the continuous valve, but it is not producing, you know. So at that time, you can use the intermittent.
Okay. How does the density of oil affect the pressure of gas injection? That's a question from Safi Sharif.
How the oil?
How does the density of oil affect the pressure of gas injection?
Okay. That's good. Bear in your mind, in order for the gas to be injected from the annulus into the tubing, it must be higher than the pressure inside the tubing. Are we agree about that? Yes, right? Yani, if you remember from here, 1 second, please. This is, I'm producing through this well, okay? So in order for the gas to enter from here to there, the pressure of the gas here must be higher than the pressure of the tubing here, okay? So, for example, if I have a well heavy oil, okay, very heavy, it means that the flow, even with injected gas or with the high gas liquid ratio, the flow, this gradient may be higher than this. You know what I mean? So for at this situation, I cannot inject from this point. I can only inject from higher point. Like again, why I'm not injecting, as we look at this diagram, why I'm not injecting from here? Why it's only here?
because my gas cannot go down there. Even if you have decreased the gradient with certain value, but the maximum casing or gas can reach here, can reach here. It cannot reach more than this. So in this scenario or this situation, you cannot inject gas from here. When can you inject gas from here? If the reservoir pressure decreased, if the rate decreased, if you have lighter fluid. So for sure, when you have higher density fluid or higher density oil, it will affect your point of injection. So at this scenario, in order to inject at a deep point, either you have oil with accepted density, or you have to have higher casing pressure here. Hope it's clear now.
Yes, it's clear. It's clear. We have a similar question asking basically about injection pressure with regards to depth and viscosity. If it's increasing with depth and viscosity.
Yes, exactly. So, you know, sometimes in order, the maximum or the optimum thing is to normally what happens, or if I have this well, 1 second, I prefer to put it with. Okay, it's the same. It's quite. Normally, the optimum, the maximum point or the deepest point that I can inject from is just above the bucket, right? Because in order to inject gas, I must have isolation between here and there, right? So the maximum point I can inject from is this depth, right? But is my injection gas pressure is able to reach this depth? No, not in all values. Sometimes, yes, it can reach here. Sometimes, no, I can inject from this valve or from this valve. You know, in Gaber, we have a platform. In this platform, we inject only from the second valve. Another platform, some wells in it, because the wells is less viscous, less dense, and the reservoir pressure is low, I can inject from this valve. So it depends. Sometimes, bear in your mind, the value of the injection gas here, you cannot control it because it's controlled from the compressors. Normally, when you start your gas lift system, you build the compressors and it can give you certain pressure. Sometimes you make adjustment to this to increase your high pressure, but still it's, you know, something like the separators. It's constrained. Is that clear?
Yes, I think it is.
Yeah.
There is another question about yes, gas lift design and evaluation. He says, Socrates, do we have to analyze the installation of each well while it's performing satisfactorily?
Normally you mean do I have like to do gas lift survey or not? Normally, normally any intervention, it's a risk. A good engineer is the engineer that's trying to do optimization. Optimization means I don't want to risk my wells. It's not good to from time to time to go inside the well, because sometimes I'm going inside the well, I lost something, something happened, whatever. So for me, I'm not wanting to go to the well. So if the well is performing well, and I know from the parameter, from the temperature, from everything that this well is good, why do I have to do some gas lift survey? No, I don't. But I do it when I suspect some problem. When, for example, I'm producing from the well, then the parameter changed. The temperature is supposed to be 100, now it's 90. The well is supposed to give me 1,000 barrel, now it gives me only 600 barrel. You know, it's something like this.
Okay. Yeah, exactly. And I think he was meaning like if I have a gas lift system in place and I have good data, if I have to redesign or something, like analyze my data every day. So I think you cover that. Now I have two questions. Says how long distance between each valve, and why which is the reason we have many valves. And before you explain, I can show this for people who can see. This is a valve, if you can see it. This is a gas lift valve. That, as engineer Ahmed said, it's a valve that was taken from a well because it's not working. It's a well intervention. with a slick line or a wire line, because we have several questions about that. But you do it only if you have a problem, because you have to stop maybe the production and other things. So, and Zanir, Ahmed, if you could answer about why we have many valves and which depths.
Okay, so we have many valves. As I said, I have valves because I'm doing unloading. So as I mentioned, I'm producing, or my operating valve is valve number, let's say, for example, here. This is the valve I'm operating from, for example. What's this again? Like put it here. I have 4 valves. This is the valve that I'm injecting gas through. I have 3 valves here. The objective of this valve is to help me during unloading. And they have also some objective, like sometimes I'm producing from this, I'm injecting from this valve now. By time, maybe like my pressure increase, I'm doing water injection or whatever. So maybe I'm now injecting from shallow valve. I don't need to inject from here. So it's something, it's flexible. But the main is, for example, if I'm designing my well and I know that I'm injecting from this valve, I have these valves to help me through unloading. Rather than each time the well dies or I have completion fluid or whatever, I go bring coil tube doing unloading. That's what I mean? So this is one thing. Regarding the distance, normally you will find that the distance depending on this curve, and it depends on this curve, it depends on, sorry, the casing pressure, and it depends on this static gradient. But normally you will find that the first valve is always at 2000, 1050, 2050, something like this. It depends more about the casing pressure. If, for example, I have a high casing pressure, then the depth of my valve will be deeper, the first valve. If I have low casing pressure, then the depth of my first valve will be shallow. The distance between valves is decreasing by time. Yani, if we look at this, for example, you will find that this is an actual gas lift design. You will find that valve number 1 is at depth 2200. Valve number 2 is at 4000. It means the distance is like 1800. Then valve number 3 is 530. The distance between them is 1300. As time you see, the distance is decreasing. Normally, you are doing this design until you reach a certain value. For example, if the distance between the valves from design is 400 feet or 500 feet, it's okay. We don't continue the design. We just making like introduce valve with a certain distance between them, which is 500 feet or something.
Okay, thank you. Is it economic and safe to install gas lift for old wells with suspected integrity problems, conditions to recover dead wells as the gas is available and cheap? If no, what is your best recommendation for wells with gas and high water cuts?
Okay, first, when you say that I having an integrity problem in a well, so you have to see, can I live with this integrity problem or not? Also, what will be the lifetime of this well? For example, anything you are doing in the oil system or the oil industry, you have to say, I will do this with that cost. Okay. In GAPCO, for example, I have a well. Is not I didn't introduce gas lift in this well, and now I want to introduce gas lift. If the well initially doesn't have gas lift mandrel, so I cannot introduce gas lift. So I have to pull the completion and put a new completion, right? So at this time, I need a rig. I need cost. What will be cost of this workover? What will be cost of this rig? This is one thing. And how will be the reserve of this well? So I have to put the cost and the reserve and the benefit and do this. I cannot enter this like this. If for example, you have this well with this issue and you have, you know what is the lifetime of this well, and you can, let's imagine I have a well, it have a casing problem. I know that it can live like 4 years or 3 years. Okay, I can, and I know that I will do some change into the system. I will introduce gas lift either with tube, with workover, through tubing or whatever. So I need to know. I will put in this like 1,100,000 whatever, and I will produce for these 3 years. I will produce like 1 million barrel of oil or 0.5 million or 1.5 million. What is the cost of this? What is the benefit of this? And what is the cost I spent? And I can do my decision. Normally in GAPCO, I have a well. I need for example, this well having a problem. I must do work over. So this work over cost me $2 million. Okay, I do my analysis and I found that this well will produce 500 barrel with zero point 0.3 or 0.4 reserve. The benefit of this will be 5 million, and I having a cost of 2 million, then this well will be beneficial. Something like this. So I have to do this economical study. Got it?
Yes. It was very clear. In overall, which is more efficient and less expensive, continuous or intermittent gas lift? What are the difference?
Yeah,
What we should choose?
Okay, continuous. We all want continuous because continuous, for sure, it means I'm producing. When I'm producing in a continuous way, then it's smooth. I don't have surge. Like the problem of intermittent, that I have the tubing head is changing from value to value. It can affect. I'm not producing smooth way. Another thing, for sure, intermittent, it means I'm not producing with high rate, with low rate. So the most efficient and the most good is to produce continuous. But in some scenarios or some cases, the well is not producing continuously. So I'm forced. And the optimum is producing naturally. I don't want to invest money and make the well producing with artificial lift. But the well cannot producing economically or cannot producing what I want in a natural flow. So I have to introduce gas lift or artificial lift to make it produce economically. So it depends on my situation. So for me, the best is continuous, but as I told, it's not in my hand. I'm forced to do it.
Yeah. I understand. We have several questions about the lifespan of the valves, of the gas lift valves or the dummy or the orifice or whatever, and several questions like that, which I think depends from the case of the reservoir and the well.
No, normally the lifetime in GAPCO, I saw wells with the gas lift system and the valves for a long time, for 15, 20 years, 25 years. I saw it. And I saw some cases like a problem happened in the valve and from the first day it's not working. But normally the time span or the lifespan of valves is long, okay? If you compare valves or the gas lift system with ESP, for example, normally we have a study before, like normally the ESP lifetime is like 2 years, 1.5 years, something like this. Gas lift is good, and one of its advantages is flexible. It have high long lifetime. It's flexible, as I mentioned, it's cheap. But the main problem is two things. First, you have a maximum drawdown you can inject. As I said, you have a certain gas left, you have a certain drawdown, the maximum drawdown that you can produce, because you have many constraints. You have the high casing pressure constraint, the flow gradient. So on the other hand, for example, ESP, you can produce with very high drawdown, with very high liquid rate. So, everything you have, it's good and bad. So at the end, you try to. So what next?
Next question. I don't know how much I can ask you. I don't know, Omar, how much time is left.
We can extend for 5 more minutes. You can take 3 questions, man.
Okay, thank you. How much the gas lift techniques improve the recovery rate of a reservoir?
That's good. We have a well, okay? This well is natural. It's producing until the water cut reached 50%. Good. Then it stopped. It's not producing. When you introduce the gas lift, it can produce until the water cut reached 90%. So this time, from 50% to 90%, you have reserve. The well is producing, and all this reserve is added to you. So you increase the recovery. Before, without gas lift, for example, I will produce 1 million. With gas lift, I will produce 2 million, or 1.5 million, or 2.5 million, whatever. So, logically, it increased my reserve. It increased my recovery.
Yeah, so this answers, I guess, the question about what would you use in a natural flowing well. If the well is offshore and it's a natural flowing, I guess you wouldn't start it directly with gas lift because you can start also.
Bear in your mind, if I have the gas lift facilities, because I mentioned at the beginning, for the facilities you have the compressor is big, the lines, you know, all this. If you have the facility, but what if you have only one platform, you don't have these facilities? Sometimes you, يعني in Gapco, for example, we have a platform that is ESP. Why ESP? Because it's near to the shore. I can put or deliver an electrical line to it. It's high viscous. I need hydro down from it. So, you know, it depends. Another, for example, platform, you don't have a gas line for it. So maybe you use jet pump or use PCB. So it depends. Normally for offshore, if you have these gas surface facilities, it's a good way to do gas lift. So the same, it depends.
Okay, let's take a final question. As Fru Hamza says, and I have to say before I ask this, that we have a very diverse audience. I see people from India and from many other places. So we're really happy about it. Yeah. Hamza asks, as we know that the injection pressure of gas lift is much higher than the production pressure, the tubing pressure.
Yes.
Does this difference can be an obstacle for the production or stop the formation of fluid from flowing?
No. It's not an obstacle. On contrary, I'm producing. How I produce? The reservoir pressure is high. It's like 2,000 psi, 2,500 psi, whatever. It produced until I reach the sand phase. I have. Let's start with. 1 second, please. My first slide here. Here I have my reservoir pressure and here I have my BWF. So in order to reduce, I have a certain drawdown until here. For example, imagine here I have 1,500 psi and my reservoir pressure is 2,500. Like I have 1,000 drawdown and I'm producing 1,000 barrel. Okay, this 1,000 is going up here, starting from 1,500 psi, and they lose pressure until they reach here the tubing head pressure. Let's imagine my tubing head pressure here is 200. Okay, so I'm producing here. I have a BWF here of 1,500 until I go up and have a tubing pressure here with 200. Then this fluid is moving, separated and stuff like this. Then I have my gas here, the 200 psi or 100 psi gas is compressed. The pressure is high. I make it reach 1,000 and then I start to inject it from here. But why I make it reach high pressure? Because I wanted to inject it here, deep. Here, a deep depth here, the tubing pressure is high. I started with 1,500 here and goes up, I lose pressure. For example, here, my pressure is 800. So in order for gas to be injected at these depths and go from the annulus into the tubing, it must be higher than 800, right? So it goes back and it injected here with this pressure and goes here and mix. So no problem. On contrary, I cannot inject unless my gas have high pressure, have high injection pressure. Here, in order to inject at this point, I must have casing pressure higher than the pressure at this point, in order for the gas to be able to go into this direction.
Okay, thank you a lot, Engineer Ahmed. I think with your answers, you covered also many other questions.
That's great.
Because it was really clear and explained very well. Thanks OPA for this webinar, and I hope we will have also future collaborations on MAR. And I would like to thank you all for attending today's discussion. And there will be way more in 2021, both from us here in Technical University of Crete, SP student chapter, and OPA, of course. And don't forget, please, to take the short survey sent to you on the chat box. And everyone have a good night and good 2021.
Thank you, Marius, a lot, and thank you all. And I hope that you all get the maximum benefit from it. And inshallah, and see you all in other webinar or other presentations, inshallah.